Over to you.
Okay. Yeah. Thank you. And I will show you my desktop first. And
Sorry, I'm late.
Can you see my PowerPoint?
Yep.
Okay. And, good morning, everyone. My name is Jinyu Gu, and I am a doctoral candidate from Shanghai Institute of Ceramics. And today I want to share one of my work, which is about the oxidation behavior of the zirconium cobalt antimony based half-use-low materials. And I will present my report from 4 aspects. And as a sustainable, green, and clean energy technology, high-temperature thermoelectric materials have broad application prospects in these fields, and the half-use-low materials have high ZT values, and the device efficiency can meet the basic requirements of applications. And the zirconium cobalt antimony system has attracted widespread attention due to its excellent material and device performance.
Sorry to interrupt, but guys, I already saw this first presentation, so feel free to ask any questions you have, okay? I already had one meeting with Jinyugu last week.
Yeah. And however, the practical application of device should consider the stability in the working environment. In an oxygen-containing environment, especially at high temperatures, oxidation leads to structural defects in materials, which is a serious impediment to the long-term stable operation. The zirconium cobalt antimony-based materials with excellent performance and have poor oxidation resistance. Therefore, we need to clarify oxidation mechanism and establish service protection technology for them. And this work takes this component as example, starting with the oxidation masking experiment. The materials were found to undergo a special oxidation process transformation. The masking is linearly related to the oxidation time at lower temperatures, while it follows a parabolic relationship at higher temperatures. And this special transformation leads to a fast and uncontrollable oxidation rate in a low temperature range. Then we carried out morphology characterization to understand the oxidation mechanism. And it was found that in low temperature region, the material undergoes external oxidation, generating the AOL formed by alternating arrangement of oxides with a large number of defects, such as pores and cracks. And in the high temperature zone, the material undergoes internal oxidation, generating a cobalt antimony layer and DOL, a dense oxide layer named DOL, formed by mixing cobalt antimony and needle-shaped zirconia. And in the mid-temperature range, masking also follows the parabolic relationship. The material undergoes both external and internal oxidation, and the typical oxide layer morphology of which, namely AOL and DOL, also appears simultaneously. And it can be concluded that as the temperature increases, the oxidation gradually transitions from external to internal oxidation. And AOL cannot block oxygen diffusion, while DOL can. And we then performed the first principles calculations in thermodynamics. The formation enthalpies of different oxides in DOL vary greatly and thereby determine the oxidation order. So oxidation reaction will proceed in 2 steps. And by calculating the Gibbs free energy of the 2 reactions as a function of temperature and oxygen partial pressure, it was found that the conium and hafnium can be easily oxidized, while cobalt antimony is only oxidized at low temperatures or high oxygen partial pressures. Therefore, the cobalt antimony can remain unoxidized and coexist with the conium and hafnium in DOL. And through the analysis.
One second.
Okay.
Go ahead.
Hi, Jinyu. Sorry I was late. My Zoom was updating. Why are your reaction not stoichiometrically adjusted?
Sorry, could you repeat your question?
Yes, equation 1 and equation 2 are not balanced. Why?
The question 1, this you mean the
Yeah.
You mean the reaction?
There is more zirconium on this side and on that side. The stoichiometric coefficients, the coefficients are not adjusted. Why?
Coefficient? Oh, you see the 1 is adjusted. It's 1 the conium cobalt antimony and 1 oxygen and 1 okay. And the chemical reaction has to perform type. 1 is
Yeah, you're just missing 1/2 on the right hand side, right?
Yeah, I just not show the coefficient before the component, but in my calculations, I consider it. I just for the simplification, I don't show it in the slide, but in my calculation, in my calculation, I consider the coefficient of in the reaction.
Okay. Please continue.
Okay. And through the analysis of the thickening rule, it was found that the pattern of the thickening of the total oxide layer is consistent with the mass gain, and a certain thickness of DOL is a key to the parabolic law. And the first principles calculations of dynamics were conducted. The diffusion barrier of oxygen and the conium in oxides are much larger than in other compounds like the conium cobalt antimony and cobalt antimony. And it can be concluded that oxides in DOL or outside the cobalt antimony layer played a key role in inhibiting the diffusion of oxygen and the conium.
So how do you define the diffusion path? What's the definition?
Diffusion barrier or
no path? The x-axis.
The path. Oh, I use the CINEB. combined with VASP to calculate the diffusion path.
Yeah, for sure. But like, what is the definition?
Definition?
Yeah.
Well, I use the oxygen vacancy as oxidation defects in oxides, and in the other compounds without oxygen, I use the oxygen in it, an oxygen atom in it, in the compound.
Is it like the reaction coordinate is similar?
Reaction
coordinate, yeah. So you're tracking the movement of a certain atom, in this case oxygen, through the unit cell. Is that it?
Yes. I calculate the oxygen movement parts in the cell. Yeah.
Okay, I understand. Thank you.
And okay, I continue my presentation. And from the above conclusion that DLL can inhibit oxygen diffusion and provide the surface protection, we designed an in situ oxidation coating, pre-oxidizing samples at high temperatures in air to generate DLL in advance. The samples were then subjected to oxidation experiments. It was found that the mass gain during oxidation was close to zero, while the thickness of the dense oxide layer remained unchanged. And at lower temperatures, in situ preparation of DLL exhibits significant antioxidant effects. And well, that's all about my work sharing today. Thank you. Thanks so much for the guidance and assistance of my teachers and group mates. And next, I want to share one of my ideas on thermoelectrics.
First, let's take a break, and anybody have any questions on the previous presentation?
Yeah, why this astroloy, zirconium, antimony, cobalt antimony shows high GT performance compared to other astroloys?
Compared to the other half-fuse
why?
system?
Yeah.
Why I choose, sorry.
Yeah, why this zirconium is important. It's been shown in literature as well. So why it is higher performance in zirconium, cobalt, antimony?
Why I choose to study its oxidation behavior?
No. Why it shows the high performance compared to other astroloys?
Why I choose this in my study?
Why this material show high performance compared to other astroloys?
Okay. I understand. You want to ask why this material have high performance? Well, the first is it is the I think it mainly depends on its electronic band structure and the phono band structure. And well, I think the Conium cobalt antimony system thermoelectric properties is not higher than the niobium iron antimony, but in the P-type materials, it is good, and its performance is enough for the application. And why its device efficiency is higher than the well, the other p-type materials, I think it is because it's mature, very layer selection.
Okay.
Yeah.
Okay. Is there any structural transition? Typically, there's some martensite to martensite transition osteolysis. Is there any transitions in this compound?
Sorry, could you repeat your question?
Yeah. Is there any structural transition in this compound? Yeah.
Is there some
phase transition? Is there a phase transition in the material?
phase?
Transition. It goes to high temperatures. Is there a phase transition?
No. Most Hapucillus don't have the phase transitions through the large temperature region. Most Hapucillus are, well, with high thermal stability at high temperatures. Yeah.
Yeah. I mean, one last question. You generally intentionally oxidize these legs, right? To avoid the further oxidation. Instead of doing further oxidation in sintering at high temperature, can you just coat with some thermal oxide, like stable thermal oxide of those legs will helpful or no? Coating any other thermal oxide on these legs will prevent also oxidation, right? Will that helpful or this way is much better?
Sorry, could you repeat your question?
To avoid the oxidation, you preheated to those legs to high temperature, right?
Yeah.
So instead of doing that, if you coat the oxide layer with some other oxide layer, the stable oxide layer on those legs will be advantage than preheating.
Oh yeah. Actually, except for the pre-oxidation at high temperatures, if we put the sample in a low oxygen partial pressure, maybe at only 800 Kelvin, it will also generate the DOL only, because this Gibbs-free energy, if the temperature is high or the partial pressure of oxygen is low, the oxidation of the zirconium antimony will not occur. Yeah, so we can choose another method to prepare the DOL, but I choose this method because it takes shorter time.
Okay. Yeah, fine. Thanks.
Related to this slide, how you get this mass gain values, experimentally or theoretically?
Sorry, could you repeat?
You see this current slide, you have plot mass gain versus oxidation time, right?
Yeah.
The green, is it experimentally measured or theoretically calculated? And how you calculate the value of mass gain?
How I
get mass gain.
The mass gain on the y-axis.
Yes.
The mass gain.
How do you get that?
How I value the mass gain of the. I put my sample into the furnace for some time, and I put it out to weigh my samples, and after the weigh, I put it in the furnace again for another time's oxidation experiment, and like that.
Okay. Okay.
Oh, okay. Thank you.
Any other questions?
How's the thermoelectric performance with this gain?
The skin, how the thermoelectric performance.
Yes.
Oh, the outside layer will not influence the thermoelectric performance of the materials. You can consider it as a layer without thermoelectric properties. Just
It's just like a coat.
Yeah.
It's just like a coating then.
Yes.
Okay.
Can you show the segmented thermoelectric device work you did?
Yeah. Show it.
You showed me last week that you did some work with segmented thermoelectric device.
Yeah. Well, it is in my previous PowerPoint. I will show you.
I asked her to give a shorter presentation, but there was something she did.
Yes. Yes.
Yeah, please just describe this very quickly. Based on the oxidation, what did you do to change the design of the device?
Okay. Just I study the influences of the different dopants on the materials oxidation behavior and the oxidation rate and the oxidation resistance. And this figure is describe the results of my study. And the high concentration of titanium doping in the zirconium cobalt antimony materials will avoid the rapid oxidation of the material. And the oxidation resistance is high. And then we have segmented doping lag design for the better thermoelectric performance and the higher oxidation resistance of the thermoelectric lag. And we put the high concentration titanium component in the low temperature region and the high hafnium concentration component in the high temperature region to avoid the severe oxidation of the materials. And the output performance of the thermoelectric lag is like the segmented lag avoid the severe increase in the internal resistance and the sudden drop in output power.
How you make this lag like titanium 0.5 below and hafnium 0.5 above?
How I connect the two materials or
these two different materials?
Yeah. I just use spark plasma sintering to sinter these two materials together.
Okay. Okay, thanks.
Okay. So if I understand, the design concept is you can take the oxidation rate and you can introduce the right transition metal at a particular temperature. You calculate the oxidation rate, and you expose that segment without drop in thermoelectric performance at high temperature. Is that correct?
Yeah.
Do you have more?
Okay, any other questions?
Can I see the thermal performance of these two materials? I didn't see. I just see the slide. Top.
This is in here. The low temperature is here, and the
Titanium.
high temperature is here. This is the ZT, the maximum ZT.
I
The
don't see
low
that. Okay, because I don't see temperature mentioned here.
And
Okay, it's here. Okay.
yeah,
Okay.
the temperature is
Okay. Ken, thanks.
And I had a question on the very basic. So I see your simulations. So you have been using the reaction energies from the half-Hashler alloys to oxide, the delta G, as a thermodynamic metric to measure the easiness of the reaction. And you have also used the diffusion activation barrier, which is an energetic term, a kinetic term. So could you please comment a bit? What do you think? So how much each of these can contribute? And because although these very much agree with, I think, what you are doing right now. So, but do you think which one is more important here, the kinetic one or the thermodynamic one?
Well, what do you want to ask? What I think is matters?
Yes, because you have measured two parameters here in your presentation. One is the energy barrier of diffusion, and the second is a few slides later. You have at different temperature. You have the reaction Gibbs free energy delta G. Right?
Yeah.
Yes. So I think eventually you want to use these two numbers to talk about the same thing, the easiness of forming oxide, of forming diffused oxide, in my point of view. So in your opinion, do you think delta G is the key factor or EA is the key factor?
I think the diffusion energy barrier is a key factor because the Gibbs free energy is to explain the thermodynamic reason for the DOLs. For the phases in the DOL, because in DOL there is cobalt antimony and the zirconia or hafnia's coexistence. So I use the Gibbs free energy to explain why the cobalt antimony will remain unoxidized and coexist with the oxide. Yeah, but
understood. And here, so at the delta G page, so what's the origin of using full oxide, say ZrO2 or HFO2 to do this simulation? Is it kind of measured by something? So after oxidation, you perform this full oxide, or some other reason?
Yeah, I see it in the XRD result.
Oh, you see in XRD, okay.
Yeah, yes.
Okay,
like this. And as for the barrier layer, I think it is more important to the kinetics. Well, and later I did some study on the influences of the dopants on the oxidation behavior or oxidation rate. And there is some doped zirconia in the DOL. So I use the energy barrier, the diffusion barrier is, they are different, and they can help me to explain or predict the oxidation rate or diffusion rate of oxygen in the DOL.
Sure, I understand. And another question is more about experimental. I looked at, I think it's something like an elemental mapping in certain page. I forget about, I think it's in your XID page.
Yeah.
Yes, and yes, in the XID page. And what I kind of find is that your oxygen is very uniform. And I'm not sure, but what I typically understand as a process of surface diffusion, the oxygen will have a profile from the top surface to the bottom. And can you explain a bit why this is like so evenly distributed here?
Just the do you want to know why it is like an alternating arrangement of oxides in the LL, or do you?
The depth, is it along the depth or is it on the surface?
On the surface.
So
it's on the surface.
Yeah, surface, and it is the matrix, and it is the oxide layer.
Oh, okay.
Yeah, and it is the surface.
why is there an oscillation?
Why is
it up and down? Why is like this? Why is it like that?
And it is because the oxides. Well, the higher oxygen concentration is when the conium or hafnium is reached, and the lower is the cobalt antimony reach, and the alternating arrangement of oxides leads to the up and down. And why there is the alternating arrangement? Well, I think it is because the opposite diffusion of the conium and oxygen in the ALL or in the external oxidation process. Because in the literature, the oxygen will induce the conium or hafnium to diffusion outside to react with oxygen to be oxidized. And if it diffuse outward and the cobalt antimony remained in it, so the green. So there is the sublayer of the cobalt antimony oxide, and the alternating arrangement existed.
Okay, I understand. Thank you. Okay, so maybe in the interest of time, let's go to your final, like the presentation on the future idea, and the summary of the paper.
Yeah. Then then I continue to share one of my ideas on thermoelectrics. It is about high entropy engineering of oxide thermoelectric materials due to the low cost, high oxidation resistance, and the low thermal conductivity. The oxide thermoelectric materials are promising for applications such as industrial waste heat recovery at high temperatures. However, the poor electrical properties and the phase instability need to be improved. And I believe that through the high throughput solid phase synthesis and machine learning as assisted component design, we can regulate local chemical bond and the gradient doping to optimize the thermoelectric properties. And this is a paper published on Nature Communications in 2024. It is about the perovskite thermoelectric materials. You use the high entropy engineering as well, and they, but they grow fields to perform the research, perform the experiments. So I think, we can use bulk to perform the high entropy engineering on the outside thermoelectric materials. I think it is promoting.
How do you improve the mobility by adding more atoms, high entropy elements?
Oh, well, I think the mobility is depends on many things. In the literature, they use to adjust the dopant to make the structure unbroken. So they improve the mobility with the scattering bonus. So I think in my idea, we can just use the similar methods to improve the electrical properties. Similar but not the same, because the article performed the experiment on films, but I think we should perform it in bulk or some, because in the industrial waste heat recovery, we should use a certain thickness to maintain the temperature difference for the application. So this is my idea.
So how do you propose to choose the dopants? What would you choose and why?
I think we can use the high throughput synthesis and machine learning to assist the component design. Because
can you elaborate? Can you tell me how? What do you want to use? Regression, classification, LLMs? What do you want to use? Or what do you think you could use?
I think if we want to improve both thermal and electron transport properties, we should choose some dopants, like in the same group or the same period to ensure it can be doped and the phase stability is not broken also, and then we can use the mass fluxion or the ice fluxion to improve the thermal transport.
Okay. I have a follow-up question. I agree that you have to do bulk. You want to do bulk because you need a length, right?
Yeah.
So you need to press. You need to SPS, right?
Yeah.
But SPS is reducing atmosphere, and you're doing oxides. your oxides are gonna get reduced. So the oxygen stoichiometry is gonna change. How do you think, it's a big problem, but how do you think we could work this out? How can we solve this issue?
Well, I think we can change the atmosphere when we SPS, or we can just after SPS we can add some annealing steps.
Mm-hmm.
Yeah,
Okay.
use different atmosphere and some temperature, some time to adjust the oxygen continue or oxygen vacancy concentration or some.
Okay. Yeah. Thanks a lot.
Just another question. This oxide mostly is N-type thermoelectric material, right?
Yeah.
So how you improve the mobility just by playing with the cations, because their structure is mostly controlled by oxygen here.
Sorry, could you repeat your question?
Okay, so I believe this all oxide materials are N-type thermoelectric materials, right?
Yeah.
So mostly the band structure is controlled by oxygen here.
Yeah.
Do you have band picture here for you? Because then how you improve the mobility just by playing the cations?
How I improve the mobility?
Yeah, but by playing
Let
with
me rephrase. The question is, because it's N-type, oxide-based materials tend to be N-type.
N-type, oh.
Right? And then if it's N-type, the band structure is usually controlled by the oxygen or the oxygen bonded states. How would you then control your doping, let's say, by introducing cations? By changing your cations. That's what you're proposing here, right?
Yeah.
How do you think that this will change with just the cation? That's the question.
How I change the mobility to adjust, I think, yeah, the dopants will change the thermal transport properties, but the oxygen atom and the distance of the oxygen atom, or the maybe the concentration of the oxygen vacancy and I think we can just something like that. Just to adjust the how to explain? Adjust the microstructures, like the angle or the distance or the defect concentrations, like that.
How do you change the I mean, similar to the same line, how do you increase the K concentration in this sample? Suppose, say, if you want to tune the K concentration, is aligned to Pepe question, but if you choose the same group of the elements, the oxidation state won't change, right? And how do you, this is N-type material, how do you choose the dopant, and how do you change the K concentration?
Oh, actually, well, because I have performed some calculations on electronic band structure before, and I discovered that although we choose the same group to doping, but the band gap or the Fermi energy will change a little. Yeah, for example, when I doped hafnium on the zirconium side, it will the Fermi energy will move near the p type a little, but the phenomenon is can be seen in my work. I will let me find if I prepare some. Just like that. It is N-type materials, and let's see the nickel, the high concentration nickel doped materials. You can see the conductivity of titanium doped is much higher than the hafnium doped.
Yeah, I got. Could you tell me the difference between this hospital alloy and oxide? How the Curie concentration? These hospital alloys, right? Mostly are N type. How do you tune the tuning the Curie concentration is number of valency, number of electrons. So when you change the nickel or cobalt to nickel, the number of valence electrons increase, right? If you increase the nickel content, cobalt, nickel, copper, zinc,
yeah. If I increase,
this is different from our oxide materials. Do you know the difference between hospital alloys, tuning the Curie concentration, hospital alloys and oxide materials?
Yeah, because Hafusler is it can just I think the doping limitation is larger than the oxide materials, because as when it is the same group, the hafnium can dope 50%. It's a high concentration, but in the oxide thermoelectric materials, I think the doping concentration can't achieve this maybe around 50%, and it is the difference between the Hafuslers and the oxides, and I think it is the biggest difference between it. And it typically seems that the Hafusler doesn't have oxygen, so the defects like the vacancy or some defects will not be seen in Hafusler, and it will not influence the thermoelectric properties in Hafuslers.
I mean, in Hafusler alloys, there's no cation and anion. It's like number of ions increase, number of electrons increase. Whereas in oxides, there's a cation and okay. Oh yeah, please go ahead.
And do you have another question?
Regarding the paper? Yeah, go ahead about presentation.
Oh, okay. And this is my idea, and if there are no questions, I will move on. Then I want to share a paper published on Nature Synthesis about a new guiding principle offered to robotic labs based on the selection of proper paths in phase diagram. And synthesis is a bottleneck in materials discovery and manufacturing. Due to the limitations of traditional synthesis methods for multi-component oxides, the article offers better guiding principles to robotic labs. And this picture shows the proper paths for synthesis, and this article can obtain more pure materials in lower temperatures. And they use the thermodynamic strategies like initiate reactions between only two precursors, and use high energy or unstable precursors. And this strategy is related to the fifth, maximize inverse Hall energy. And then target should be the deepest point in the convex Hall. This and this is right, and this is not so good, and minimize the competing phases in reaction paths. So this is suitable for the thermodynamic strategy, and the convex Hall was collected from material project, and they use the robotic lab for validation. And as a result, the new guiding principle succeeded in most compounds, around 91%, and the robotic lab enabled rapid and reproducible testing at scale. And it proves the great potential of accelerate development of functional materials.
So, I'm sorry, please go on.
No, go ahead.
Thank you. Sorry to interrupt. So you said that it succeeded in most cases.
Yeah.
Why did it fail? Why? What happened?
Because it only will consider the thermodynamic calculations and not consider the kinetics or the diffusion things. So, and maybe like that, if the thermodynamic driving forces is not big, it will fall too, because I think they calculated the material project calculated in the 0 Kelvin. It doesn't consider it at high temperatures. So it is maybe the one of the reasons it's not succeed in some compounds.
So how would you, okay, thank you for the answer. So how would you use your work, the work that you've done, to improve this?
Improve this? Well, for me, I will add the diffusion barrier layer calculations.
Okay.
Like, yeah. And I will maybe use the thermodynamic in the different temperatures, because in the literature at the entropy, they consider only they don't consider the they don't consider the vibration entropy. Well, I think I can use a phonopy to calculate it. And it will give me the results in at high temperatures about the thermodynamics.
Okay.
So the key idea you mentioned here is that they use the driving force, and the driving force is calculated based on 0 Kelvin temperatures. And you think by including the vibrational entropy, you should be able to improve these predictions. Is that correct?
Yeah.
How does this relate to the idea that you presented earlier? Let's say high entropy oxide thermoelectric materials. What can you combine these two? Let's say if you want.
Yeah, I think I can, because they are similar in synthesis. Well, both oxides and both multi-component oxides. So I can predict the synthesis results by using this thermodynamic strategy to obtain a single phase high entropy oxide materials, I think.
Any other questions? I'm just mindful of time, but we can take one last question. Okay, if nothing else, then thank you, Jinigo.
Thank you.
Getting all of these. Do you have any questions? Last questions for us?
Sorry. Well, I want to know how often you cooperate with each other. Well, if we meet some difficulties in our research, will you ask for help immediately, or you just handle it yourself for some trying, and then ask our group mates or teachers for help?
Maybe the group members can answer that.
Yeah.
I don't know the answer.
I mean, we are very collaborative. We discuss our results together, and we generally give some feedbacks from other group members as well. We are kind of team, even though we are single assigned projects, but we are very cooperative in that. Yeah, please add.
Thank you.
Please add.
Thank you.
Anybody else wants to add? I mean, usually we meet every 2 weeks as a group. But,
Yeah.
Apart from that, I think everybody works in the lab. So if you have any problems, there are separate sort of WhatsApp groups where people chat, and many people are in the lab. I think in general, it's quite collaborative.
Thank you.
Okay. If nothing else, then thank you, Jinyo, for taking.
Yeah, thank you. Thank you all.
You can drop off from the call, then we can have a discussion in the team. Thank you very much.
Thank you. Thank you. Okay.
View. Okay, thank you. All right. I removed her. I didn't know if she got it. Oh, I asked the guy to join 15 minutes late. So we'll just take like maybe a quick 5-minute discussion. If someone can take notes. What are your thoughts? Maybe just I can take notes. Maybe just say.
I'll take notes. No worries. You can chat with the guys.
Yes, people can take the notes.
Quick thoughts.
An understanding of Astralize is good, and the study is very systematic. Whatever she did, not even analysis and kind of where she failed, she could back improve the performance and everything. Study wise, studies is good, presentation, old literature, but understanding on the oxides is not. Understanding new system is not completely different from Oscar Lois. She's not really aware about other systems. I mean, based on the presentation, but she's good in some advantages, first principle calculations or some oxygen. Those calculations are unusual. Experimental list has, so she's good in that. Maybe useful for us. That's my feedback. Yeah, please go ahead.
Any other thoughts?
Yeah, same to Mahesh line. I think understanding wise, physics understanding is still not that up to that mark. Maybe she can improve. I don't know at this point. Yeah. Understanding the data wise a bit.
I mean, communication is not issue. Communication she can improve. She will be fine, right? All people here after they came is very good.
For me, I think I fully agree with whatever Mahesh has been saying. The only concern I kind of have is it's pretty apparent that his current research project on coating oxide on the layer are kind of derivative of a very big project from somewhere, which I have no idea about. And so it's eventually coming to the end that what she is planning to do, like in the new lab. And so from this part, I'm not yet very clear on what she plans to do.
Okay. Any other thoughts?
As Pepe asked, like the question, right? How the oxides can be used in SPS. The mitigation step is also a nice idea. I mean, it's good thinking.
Post annealing or something.
Yeah, post annealing. Yeah, it should be done. Otherwise, you cannot get.
Chengwang, Jayanta, and then Pepe, and then I will comment. Okay, Chengwang?
Yeah, I fully agree with Mahesh. And because, you know, her background is the engineering, right? So I think since her research was systematic, so I think that's enough. I mean, for his field, or in her field.
Okay. Pepe?
What do you want her to do?
So I think it'll be, let's say, working on high entropy thermoelectric materials, not necessarily oxides, because we're going to use direct joule heating, obviously.
That's my first thing, like.
But it's okay because
no problem. You know, it still can be done. They do it in Gert's group. You know, like it can be done.
Yeah, I mean, but we don't need to. I mean, I think the high entropy calcagenides are probably more interesting because fewer people study it anyway.
For sure, yeah.
It's worth thinking about, and I think some initial work has been done. You've done some initial work with Christine, so I wanted her to sort of take over that and supplement in like the full thermoelectric measurements.
Okay.
So remember that material star project.
Okay.
A star, or I don't remember what I called it.
So
full
okay,
experiment.
Okay. That being said, here's my 2 cents. She did not answer the questions that were asked directly, and that's kind of a negative for me. Maybe it's the language, and that's fine. She will improve for sure, but some of the questions she answered, I like that she pointed out that the XRD and used it to guide herself in the thermodynamic modeling. But the presentation is gone, and I still don't know what the diffusion path means. Like, if it's diffusive, it's fixed law. Why doesn't it have units? If it's reaction coordinate, why don't you call it a reaction coordinate?
Yeah.
And that's kind of a negative point for me. But knowing what you want her to do, I think she can do that. In a couple of months, she'll pick it up and she'll be up to speed. She'll be better than me by the time I get back. So that's what I think.
Yeah, so my feeling is like, firstly, she's not really a thermoelectric design person. Okay, so this is one of the reasons why the physics understanding is not so good, because it's a very specific project that was given to her. But I like the carefulness with which she did this oxidation resistance. Okay, so she came up with the idea of how do we predict oxidation resistance, how do we measure it, and then she didn't show this data, but she had a whole grid of things that she measured, like full sample. She sampled the whole thing to map out the space. She did a lot of experiments. So technical skills, I have no problems, right? I don't think she can build a single leg thermoelectric device measurement. That I don't think she can do.
That I was about to ask you, like, she seems that she knows about devices, which none of us do. So that would be very positive as well.
Yeah, but I don't think she knows. She just, someone told her how to make a certain leg, and then she made the two sizes and she put it in. And some
I think, I think she's capable of, assembling the devices, the whole devices. Because as far as I know, in Chen Lidong's group, right? So what she was working on is about about the thermoelectric devices for the military usage. Actually, in Chen Lidong's group, their product value is about $200 million for the military usage every year. Yeah, so probably she was only working on how to make their product to be properly used in the military and then nothing else.
But then, like, why she didn't say I made the devices?
Yeah.
I mean, like, I agree with that. I think somebody told her how to do it and she did it.
That's my point. I don't think
I agree. I don't think, like, because if she's done it, like, might as well say it. Like, I made the devices. Here's how I made them.
I mean, she prepared the legs, SPS legs.
I think she made the leg on one leg.
Okay, fine. Preparing the leg, sure, like, fine, but like not the device.
On the device. I don't think
maybe she made the leg and somebody else in the lab. Chen Lidong's group might be big, right? So somebody else maybe made the device and measured it because that's their project. Right?
Yeah, probably.
I will reach out to Lidong Chen and for the reference letters anyway. And I'll ask this question, right? I know. Can you please explain in your letter if she made the devices or not?
Yeah.
So I mean, in general, I feel like at least she has done a lot of thermoelectric measurements, so that's good. Yeah. One of the things that we need for this project, fortunately or unfortunately, is the ability to measure everything properly and carefully, which I think she can do. It seems like a learning exercise where she would have to learn better to communicate. Her communication is not very good. Okay. Half the time she doesn't understand the question. But when she seems to understand exactly what the question is, she seems to answer. Yeah. That was my impression.
Yeah. So about that, I don't want this to come across mean or anything, but I think the importance to communicate it's huge because if we don't understand each other, we cannot work together. Or we will, but everything will be delayed.
Yeah. But
that's a problem.
I true. But I do see people change a lot in Chengyong. The discussion with Chengyong before 2 years and now is crazy.
But Chengyong is a PhD student and not a postdoc.
I know. He came here and improved.
There is a difference.
Like, so I can see so many people came here and improved like crazy.
Mahesh, yes, but Chengyong is a PhD student. This is his training. This person is coming here to do work.
Got it.
Yeah. Exactly.
Okay.
I think the different.
Okay.
The skill set that you need is different.
Yeah.
She'll have to drive a project. Let me put it this way. Can she drive a project? I'm not so sure.
Yes.
I'm going to say
doubt.
No.
I doubt.
Yeah. So this
unless you train.
She'll pick up the skills for sure.
Yeah.
I'm convinced in a few months.
Yeah.
But you put her in the lab day one.
Yeah.
And then Kedar, like, you have to get somebody to train her.
I know exactly. I don't want to do that. Stop.
Like training is great. Like I'd be happy to do it. But that's a very low return on investment on a postdoc.
Yeah, I agree with that actually. So I prefer somebody who just comes in and is able to work. Too bad because the stage we are in right now, this is a nice to have position. I'm creating this position. Okay, it's not something that we need to have right now, but so in a way, unless it really matches everything, I don't think.
Yeah. So I think
that being said, I will reach out to Lidong and get the letters. So it's I think on the fence. I'm not against her because I think she's done careful work, but she doesn't have the oomph. Like even with finally her eyes lit up at the very end. Oh yeah, I can connect this with this. It took a while for her eyes to light up. It has nothing to do with language barrier.
Yeah. Not really reviewed the paper which you shared. like how you choose the precursors, what are the steps, how you choose. Those not really explained well.
Yeah, exactly.
The paper I read.
No,
Yeah.
I mean, I didn't. You see, I'm not asking you literature review. I'm asking you, oh, what inspired? I want you to think about, oh, this inspired this idea, and then you talk passionately about something.
Yeah.
There's nothing like a little bit like, okay, I can do this and I can do that. And this is what the paper did. Fine, I get it. So it's a little bit on the fence for me. I'll get the reference letters and
yeah. See what Lidong says.
Yeah,
like.
Yeah. Anyway,
Make a decision.
I haven't even advertised the position yet. So this is actually came from a secondary recommendation. So I'd rather have somebody who is driving their own project. But yeah, the other problem with this is that they also need to be able to work in the lab. Sometimes people who drive their own project, they don't work in the lab. So that's also the risk that you have. So this is clearly not the case here. She clearly has, done a lot of work in the lab and she's able to take care of her own.
Yeah.
She will.
I think she would be very good in the lab.
Yeah.
Yeah.
This is the one good thing. I think be very careful. We need this very careful sort of data collection for that project. The idea is already there. So, maybe it's a good. So this is why I'm on the fence, personally. Okay. So, okay, let me get the comments back. If you guys have any other thoughts, please message me, okay? And then we'll see how it goes. Okay, let's take a quick 3-minute break. Join the other link.
I have just texted you the notes I've taken from this conversation.
Thanks.
I think they capture what we spoke about, so you can make your decision, Kedar.
Great. Thank you, guys. See you in a few minutes. I'm going to do a bio break. I'll be back.